So this is finishing up the problem that we started in the previous video. So the first question to ask is, what is given in this problem? So we have specifically given the wavelength. We know this for two reasons. One, it says I have a nanometer, like it's given a value with a nanometer, and we know that lambda is given in a distance. So we know this is going to be our lambda. And excuse my terrible handwriting, I am just writing on a mouse pad. So this is lambda. And we also know, because we're asking for frequency, the question is asking for frequency, we can assume that that means somewhere we have to have the lambda for our current knowledge. So the second question, what do we want? Frequency. Is there anything else given that maybe may not be explicitly stated in the question? In this case, yes. So for like an exam or something, you will not be given explicitly the speed of light, but you should know it. And so how do we go from wavelength to frequency? So we know that frequency is new, and so it's basically asking you, hey, what's new? And you reply c over lambda. So we're going to be using this equation. Again, that is an equation that you have to know. It will not be given on exam 2. So we can say that new, that is my terrible version of new, is equal to c over lambda. C is given as, that's a really ugly 3.00 times 10 to the 8th. That's a 0. Oh, that 8's not so bad. Meters per second. And that's over lambda. So the third question is, what's our equation? But also, are there any conversions that we need? So if we put in 450 nanometers currently, our meters and meters are not going to cancel out. So again, unit conversion is a great way of thinking about how to set up this problem. So we know that frequency is going to be in units of per seconds, or inverse seconds, or hertz, which is 1 over seconds. So we need that meters to cancel out. So we need to convert to get those units of distance to cancel out. And you do have two options. You can convert the speed of light from meters to nanometers, or you can convert 450 nanometers to meters. It does not matter which one you choose as long as the units cancel out. For me, it's easier to think about conversions when I'm just dealing with one unit. So we'll do 450. I'm going to do that up here. 450. Okay, so 450. Got a mouse, so it should be written a little bit better. Nanometers and nanometers. Yeah. So how do we go from nanometers to meters? So we want to get rid of nanometers. So we need to put nanometers on the bottom. And what do we want? Our desired unit is meters. How many nanometers are in a meter? So there's, again, a couple different ways to think about it. But you can either say 1 meter has 10 to the 9th meters. So this should be a positive number here. Nanometers are smaller, so you can fit a lot of nanometers into 1 meter. So that should have a really large number. So when we convert this, you can type it into your calculator, or you can just move over some places. Scientific notation, we have 4.50 times 10 to the -7. I don't think that's seen on the board. And so this value should be a smaller number. So we're going from a tiny number to a tiny unit to a large unit. So there should be the final value, or the final distance should be smaller, because there's less, because we're going from a tiny conversion to a large conversion. So we type this in now. We have the correct units, so 4.50 times 10 to the negative 7 meters. I just want to point out that if we look at the units, I'm going to try to change the color. We see that meters divided by meters cancels out, and you're left with seconds inverse, or you can say 1/seconds, or hertz, either way. Go back to red to keep everything the same. As for significant figures, we have 3 here. This is an exact conversion, so we have infinite. So the answer should have 6. That means we do keep this 0 here. Our values for the speed of light has 1, 2, 3. And our values for lambda is 3, so our answer should have 3. When you type it into calculator, you should get 6.6666666, whatever, times 10 to the 14th. So if we just look at correct roundings, you have 6.67 times 10 to the 14th inverse seconds. So at this point, let's stop and analyze the answer. So we know that frequency and lambda, so frequency and the wavelength, are inversely proportional. So we have a very small value for the wavelength. So we have 4.5 times 10 to the negative 7th meters. So that's a very tiny number. So we would expect a larger value of frequency. And we see here that 6.67 times 10 to the 14th is larger. So at least proportionally, the answer makes sense. Okay. There are some more questions like this on your homework, so please take a look at that. You probably learned this in high school or in your physics classes, but here is the electromagnetic spectrum. It's not just red through purple. So the visible spectrum that we see and that we pay attention to and what our light lab was going to be about really just focus on a very narrow window in the whole electromagnetic spectrum. So you can see here that it just fills up a very tiny fraction of this spectrum. So we go back to the laser pointer so you guys can see that. We can see that the wavelengths here, the shorter the wavelengths, we can say has a higher frequency. That corresponds to the side on the purple. So if you guys remember that purple has higher frequency and lower wavelength, and red has higher, longer wavelengths and lower frequencies, you can think about the relationships between, let's say, gamma versus radar. So gamma rays is toward the purple side of the spectrum, so it should have shorter wavelengths, higher frequencies. Radar is toward the red side, and so you can think about it as being longer wavelengths. The longer the wavelengths, what we call safer. And they can go a longer distance. The shorter wavelengths are a little bit more intrusive. So you can think about X-rays. Remember, too much exposure to X-rays can be bad for you. Ultraviolet rays, of course, gamma rays, which we won't talk about too much. The visible spectrum is based on humans' perspectives. Men and women have slightly different wavelength ranges. But if the world was ran by bees, our visible spectrum would actually be closer to ultraviolet rays. So the only reason we call it the visible spectrum is because humans dominate the world. It's not visible to everyone, and you can think about different animals having different spectra and visibility. You know, dogs can see at different wavelengths, but for better or for worse. Some animals can see better at night because they can see better in the infrared spectrum, like snakes and things like that. And then we see down here a relationship between energy and wavelengths and frequencies, which we'll get to. Scale-wise, you will see several different electromagnetic spectrum. Sometimes they go from long to short, or sometimes they go from short to long. So it's very important that you don't get into the habit of just reading it left to right, actually looking at the values. So the larger the numbers in wavelengths, the longer the wavelengths, the shorter the frequencies. And I like this electromagnetic spectrum because it kind of puts you into perspective of what it visibly represents. So 10 to the negative 3 is about the size of this period. And as you get shorter wavelengths, you can see smaller and smaller particles. So we do have like X-ray photography or spectroscopy at shorter and shorter wavelengths. As you get bigger, then you're thinking on the scales of a baseball or house or soccer field or very long distance. You can see the purpose. We have radioactive materials to look at X-rays. For medical purpose, we have AM and FM radios. So for distance, microwaves, so you can heat up those particles. So pay attention to what your scale is, not just reading it left to right and hoping they're all the same. Some different units. Again, this is a nice callback to Chapter 1 material about when we use different prefixes and conversions. Not everything should be measured in meters. Again, visible wavelength and ultraviolet should be so small, and the distance between the wavelengths are so small, you should use nanometers. So you don't always have to write 10 to the negative 9th or things like that. As you get larger, meters will become a little bit too small, and you can use kilometers. When you think about radio waves, those are very long distance. So instead of saying thousands of meters, we just say a kilometer or two. When we're doing conversions between frequency and wavelength, a good habit to get to is pay attention to your units to make sure that they cancel out. Because remember, speed of light will be given in meters per second. That does not necessarily mean that your wavelength, your lambda, will be given in meters. So pay attention to unit conversions. I think I'm going to stop there for this class. I don't want to overwhelm you with too much information. It gives you a brief introduction to light. The next thing we're going to cover after exam 1 is looking at quantum mechanics and how we go from the atomic structures to our understanding of light and how those combine. We're going to learn about quantum numbers. We're going to learn about conversions between energy and those discrete levels we talked about with the Bohr model, and how we can use energy in and energy out to look at the absorption and emission and how we get pretty colors. So again, review chapter 6 in the first few sections, and this material will not be on exam